Thank you for the introduction. As he said, my name is Ashton Webster, and I'll be presenting work done by myself, Ryan Eckenrod, and our advisor, Dr. James Pertolo from the University of Maryland. The name of the paper is Fast and Service Preserving Recovery from Malware Infections Using CRIU, which is kind of a mouthful, so I'll refer to the actual project as CRIU-MR. So a lot of research is done on the side of detecting and preventing malware. This is sort of the best case scenario if we can prevent it, and it's also important to be able to detect it so that we know if there's something there. But we also need to consider sort of the unfortunate, common, but worst case scenario where you do get infected and you need to recover from malware. So this is sort of something we see a lot, and it's inevitable when you have lots of servers and they're public facing. There is some research done in this field, and most of the solutions are very good at undoing the changes that are done by malware and preserving the legitimate changes by benign processes. However, they don't usually consider the availability of the system from a perspective of how long this recovery process takes, and also whether the connections that are being made to something like a web server are preserved after the recovery process. So for example, if you're running a web server and you're aware that periodically you're infected by malware just by virtue of being on the public-facing web, you want a solution that might be able to not only remove the malware, but also consider if there's a way to preserve those connections and the processing state of the server at that point in time. So there are some naive approaches. Commonly, the way that you might remove malware is to simply just turn it off and on again, maybe reformat the operating system so that you can be confident all the malware is removed. But of course, this takes time, and you have long downtime during that. The VM snapshots are another common way, just periodically, taking images and restoring from one of those. Again, you might lose processing state after that, and you also have to keep track of if you took a snapshot that actually had malicious process on it. There are also off-the-shelf antivirus restore that can attempt to undo the changes done by viruses and malware. However, in practice, these are not very effective, and there have been many papers showing that at best they get about 80%, but often lower than that for undoing the malicious changes done by malware. So in terms of the state of the art for more robust approaches, there's kind of two categories. There's log-based and VM-based approaches. And just to walk through some of these, there's the approach TASER, which is a log-based method, and this uses taint flow analysis to see some of the changes done by malware processes and undo them. There's Back to the Future, which uses categories of trusted and untrusted processes and logs them differently to handle their behavior and maintain the legitimate changes and undo the malicious ones. There's CCOM, which is a VM-based approach, and this is sort of an interesting one because it also identifies the malware using a behavior clustering approach and is able to undo the malware changes that way. There's Time VM, which takes a network logging approach as well as the VM-based approach, and keeps shadow VMs, which are sort of like delayed instances of the current VM, but they're receiving traffic at a delayed rate, and then it just fast forwards to one of the ones that it's sure is uninfected. And finally, there's Exact Recorder, and this just sort of logs all of the non-deterministic events on a VM and uses that to undo malicious changes. So the last one I have here is our method, CRIU-MR, and I just want to compare that with some of the prior work. I want to bring your attention to the fact that many of these other solutions do not maintain active connections and also have significant runtime overhead and restore overhead. So we seek to sort of improve upon these methods in this way. So I want to talk a little bit about the design implementation here. Our solution leverages LXC, which is Linux containers, and CRIU, which is checkpoint and restore in Userspace. I'm going to talk about these more in the next slides. It's also able to preserve active connections and does the recovery process in about 3 seconds on average. There's virtually no overhead during runtime. It's just the overhead of running a Linux container, which has been shown to be very small. And it maintains or it preserves the state of the malicious processes separately so that you can analyze them later. So Linux containers are essentially they're similar to Docker, but specific to the Linux operating system. The idea here is to provide a virtualized sandbox for executing these processes. They come in privileged and unprivileged varieties. The privileged ones run as root and are not considered to be secure by Linux because if you escape from the container to the host operating system, you essentially have root user privileges, which is why there are also unprivileged containers, and that's what we do all of our experiments with, where the users on the container are mapped to random high UIDs and GUIDs and would essentially have no privileges, just a nobody user if they were to escape to the host. CRIU is checkpoint and restore in Userspace. This is essentially a software that allows you to checkpoint a process, save all the state, including memory, files open, registers, and restore them exactly the same. Critically, it also is able to restore TCP connections. So this has already been leveraged in prior work for dynamically creating honeypots for patching. And we extend on this idea for malware recovery so that we can have these connections exist before and after the restore. You're also able to checkpoint and restore entire Linux containers using CRIU. This is actually built into LXC command and calls CRIU on the back end. So the main changes that we made were to the CRIU source code, and those were broken down into both the checkpoint and restore. During checkpoint, we basically identify the processes that violate some policies, which I'm going to talk about next. But these are basically just identifying which processes are legitimate versus malicious. And then during restore, we actually do not restore the malicious ones, obviously, but we do restore the legitimate ones. Just out of the box, we kind of get the TCP restore connection functionality that's built into CRIU. We also create an agent which is able to accept alerts from any IDS, IPS system that you might have, and then it converts these to the policies and handles the CRIU processes. So these policies, like I said, are flexible enough to handle a variety of alerts from your IDS and IPS, and basically should be used to identify the processes that might be malware. The static policies are just assertions that should always hold true. So those might be things like this process should never be opening this file, or some process should never have a child. There are also dynamic policies, and these are the ones that would be generated based on alerts that you get from your IDS or IPS. So perhaps connecting to a known malicious IP address, or even like a manual alert from the network administrator. So here are some of the policy matches. Just to quickly run through these, there's executable name match, so just the name of the executing process. File name match would be if there's a file that's opened by a process that should not be. TCP IP match goes back to what I said before with connecting to a known malicious IP. There's memory match, where you can do a regular expression match on the actual memory contents that are being loaded. And then PID and parent PID match if you have something that is able to specifically identify which processes to not restore. And finally, there's parent executable name match, which goes back to some processes should just not have children. So in terms of the actual modifications to CRIU, these were done as a open source fork of the CRIU repository. And these break down to first the checkpoint section. This hooks into all the serialization of different resources. So those would be files, TCP connections, memory blocks, and we check that the policies are being, any policy violations there. The violating processes are written to this emit.image file, and we still save the malicious process state, but as we see in restore, we don't restore it. So we look back at that emit image file, we emit the processes from there, and then we also change it so it doesn't restore processes that are missing resources. So if you have a process that is able to download malware to the system and that's not present there anymore after the file system restore, that process would just be not run either. LXC, the changes here were pretty trivial, essentially just changing it so that the backend CRIU version was ours instead of like the modified version instead of the real one, and accepted the parameters that we're using for accepting policies. And we also have that as an open source fork of the original policy, repository. So for the agent, again, this is sort of the orchestration process for triggering this recovery. This accepts the JSON alerts and parses them into the protobuf formatted files that CRIU accepts for its policies. And it is, I have sort of a diagram there on the right, which shows that these alerts can come from either on the host or outside of the host and from a variety of different sources. One thing I haven't talked about yet is the file system restore. So we assume that the file system is mostly static, which might be the case for web servers where the state is managed mostly on like a database server or something like that. And then we just keep copies of the file system on the host that we know to be legitimate and simply rotate them out. So that we take the infected one and swap it with the legitimate one during the restore. So the full infection chronology kind of looks like this. We have some way that malware gets onto the system. It's detected by IDS, IPS, a manual alert, whatever it may be, and it's sent to the CRIU-MR agent as a JSON formatted alert. The CRIU-MR agent converts that into the policy, and starts the checkpoint process. During the CRIU checkpoint process, policy violations are flagged and written to the emit image. The file system is restored, as I said, by swapping out the legitimate file system and the infected one. And finally, the restore process restarts all of the non-malicious processes. Okay, so for our experiments, we have two different questions that we're trying to answer. First, the one is, are we able to remove different types of malware and how long does it take? And second, what is the availability impact if we have multiple concurrent connections in sort of a real-world web server case? So for how long it takes to remove malware, we conduct this experiment by collecting 6 different Linux malware samples and having them run for a few seconds on a fresh container state, triggering a restore with our custom policy, and timing how long it takes. We repeat each malware removal process for each of the malware 10 times. Just to summarize some of the malware that we used here, I'll let you read the slide, but essentially there's some that are mining Bitcoin. There are some Metasploit exploits that try to run shells on ports or reach back using reverse shells. And there are some just vulnerabilities in things like the go-ahead web server that can be exploited to run arbitrary code. In all cases, the malware is able to be removed, and it takes right around 3 seconds in every case. In terms of the duration for each of the steps, the checkpoint system is sort of the dominant time one, but there's also some time for restore, and the file system swap and preparation are sort of negligible in the scheme of things. So for our next experiment, we consider the sort of stress test with many users on a web server. So to simulate this, we have a variety of file sizes hosted on the web server from 1 kilobyte, 10 kilobyte, 100 kilobyte, all the way up to 1 gigabyte. And we let several users connect to it simultaneously, each retrieving different files. At the 30-second mark, we have malware execute and recover from it. And we time how long each connections take. So most of the connections are not actually going to be affected by this malware recovery process, but the ones that are will have a slightly higher time. In all cases, we find that the connections are not interrupted. So to look at the timing results here, we compare on the y-axis the difference between the max and median time. So the max is sort of a proxy for the connections that were affected by the malware recovery process, versus the median is essentially the ones that are not. And in all cases, that falls to about 3 seconds, which is, again, the time I said that it takes for that recovery process. So the takeaway here is that regardless of the file size, and even with 7 concurrent connections, the recovery time is about the same for all of these. If we expand on this, I have that same chart on the left side here, and I have 35 and 140 concurrent connections in the middle and right side, respectively. And we see that in almost all cases, it's about 3 seconds, even with more concurrent connections, regardless of the file type. Then there are a few outliers, but by and large, it appears that the recovery process is not dependent on the number of concurrent connections or file size. So for our discussion, we consider some questions about whether it's possible that a TCP connection could terminate before the policy is able to be evaluated. In that case, it may still be possible to recover from any malware on the system just based on the fact that the resources might be missing. We also return to this question limitations. But for the possibility of extending this to other operating systems, the main limitation here is other containers, to the best of my knowledge, like such as Docker, do not have this TCP restore functionality. So that's kind of the limiting factor on having the connections restored, at least. There is also potential for denial of service if an attacker is able to repeatedly have this trigger the recovery process, even if there's not malware, just as like a false positive. So this should really be used in conjunction with best practices, such as patching and just blacklisting IPs and things like that. For limitations, the primary one is that if there's a trigger, like there's an alert, but during the policy checks, there's no policy violations and there's no processes removed due to missing resources. So essentially you have an alert, but you weren't able to actually find the malware. There's two perspectives you can take. One is that, well, perhaps the alert was a false alarm, or to be safe, you can just sort of restart the processes manually. In that case, you do not have this connection recovery functionality. We also don't verify the validity of alerts. Really, one simple way to achieve this would be to have the authenticity of them checked based on signing. For future work, we've already started to consider dynamic honeypot creation. So this, instead of just throwing away the state of the malicious, or saving it for later, the malicious state, we can have that execute in a separate container. So essentially, the legitimate processes would be running on one container, and the malicious ones would be running on sort of a sandboxed container. To achieve this, we would also need to sanitize any of the sensitive state that's on the container. And some of this would be like sanitizing the memory space, which is sort of an extension of the previous work that we already did there. We also want to consider dynamic assertions, which are queries that we can give to processes to verify that they're legitimate and not masquerading. The malicious process is masquerading as legitimate ones. And we want to craft these queries in a way that only the legitimate processes would be able to answer them, like based on their calculations. And finally, as I mentioned before, the verifications of alerts and their authenticity is important to prevent denial of service. In conclusion, we're able to achieve our goal of having the connections maintained through the recovery process. We have pretty low overhead both during runtime and the recovery process. The recovery process takes about 3 seconds, and the overhead is just running the Linux container, which has been shown to be pretty effective. It's modular in the sense that it can accept alerts from a variety of sources. They just need to be JSON formatted and be able to be sent to that IP and port that the agent is running on. And all of this is available as open source on GitHub. So thank you, and if you have any questions, I'd be happy to answer them.
Nice work. But it seems our evaluation assumes the malware can be detected within 3 seconds after the infection. Is that a reasonable assumption instead of days or at least hours?
So I think it's realistic to believe that it might be longer before it is detected. So that's where, like, the policy, if whatever the policy was generated, or sorry, whatever alert was generated, it needs to be have information that can be used to reach back and figure out where the malware is still. So that should be basically the same. Assuming like at some point an alert is generated, you should still be able to trace back and find it.
But I think this will related to the performance, right?
This wasn't factored in for the timing of how long they ran didn't factor into the performance metrics that I showed here. I don't know if that was the question.
Okay.
Yeah.
Thank you.
Name and affiliation.
Jason Gianta, U.S. government. Is this work mostly focused on supporting web servers? Is that right?
Yeah, another, essentially, yes.
Okay, because there's a lot of scenarios whereby if files are being manipulated on the system and there's dependencies on those files, rolling those back would just corrupt the system. So in the case of a web server, still, going back to his question, if the detection to response of the malware being infected is after a checkpoint, you have to roll back many minutes. And so how would you handle situations where you already have ongoing, say, TLS connections, things like that with state? How are you going to roll that back and continue to have those connections going live?
So essentially, the files would be restored back, but the TCP connections would be still like based on when the checkpoint. So there's the file system checkpoint, and there's the TCP and the rest of the processing state checkpoint. So the assumption we're making there is that the files would come back to the state they were at that time, and the TCP connections would continue uninterrupted.
So for all the other processes, you're not, I guess I don't understand. If you're rolling the whole Linux container back, you have other processes in that container that have state, TLS state, and HTTPS TLS state. If you roll those back, how do you continue to have a conversation in the future for those other processes?
So the processes are kind of independent of the file system restore process. Like we're checkpointing those and kind of like restoring them exactly as they were at the end. There's no rollback
for those other processes. So you're just killing the malicious process, just one.
Essentially, yes.
Okay,
yeah.
so any sort of dependencies between processes would screw up the state of the machine. Like if you had two processes, if you had the malicious process modify a file, and then another non-malicious process was reading the file or modifying the file, how does that work?
So the file would go back to like its original state at the start of the container, essentially, or whatever like the clean state of the container is in terms of files. Mm-hmm. The processes, the malicious one would not be restored, and the legitimate one would be restored exactly as it was, like at even while the malware was running. So the one concern is like if there's malware processes reaching into the legitimate processes and modifying their memory, that would be an issue, because then you have like some process that's essentially no longer legitimate now. But as far as the files both being the file being modified by two different processes, that shouldn't be an issue, because we're going to restore that file back to its original state. The legitimate process is going to use that, and the malicious one won't be restored.
So you'll lose the delta between, and that's okay, I'm guessing? And as long as that doesn't affect the TLS connection?
Yeah.
Okay, thanks.
Hi, my name is Evan. I'm a student from Georgia Tech. This was kind of, I think, covered maybe by the previous gentleman, but I wanted to make sure I touched on it. So what happens when you have an infection that actually infects the legitimate process itself? To draw a correlation to Windows malware, often Windows malware will infect Explorer.exe to maintain some sort of persistent connection or persistence in that system. Does your system handle this? 'Cause I think a lot of it was mostly just the external processes. It'll sort of remove those. I guess, do you also just take a snapshot of the actual process itself and then roll back to before the process was actually infected?
Yeah, so there's no rollback. So if it's like changing the other legitimate processes in some way, essentially those are now illegitimate. So you can either have policies that like also would remove those and you'd have to restart them, or you would need to extend this in some way to be able to, I guess, you would need some rollback functionality as well to be able to return that to a legitimate state.
I see. Okay, thanks.
Hi, thanks for the talk. I'm Kevin from University of Maryland. I wanted to ask about the 3 seconds that you said was the approximate amount of time it takes to execute the whole restore process, and you mentioned that most of that time is associated with the checkpointing. And I was curious if you investigated what factors might scale that 3 seconds up or down.
Yeah, so I think most of the checkpoint process is like iterating over all of the different resources that are like being used by all the processes and serializing all of those to different image files, which are then restored. So I suspect that adding like lots of policies that would, well, first of all, just having lots of those resources, if there's many things that these processes are referencing, which is why we wanted to conduct this experiment where like there's lots of simultaneous connections, each kind of has its own process and its own memory and all of that. And also if you have like thousands of policies that would need to be checked, you'd have to like, for now, linearly iterate over them. So some of those things could affect the checkpoint time.
Yeah, I mean, I guess one thing that I wonder about is whether this checkpoint time is something that would be representative of a typical web server, or if you had something that was really massive, maybe it would take orders of magnitude larger than that.
Yeah, that's kind of why we tried to do the like realistic web server situation where there's many files that they're all referencing, they all have their own like processing state, then they all need to be maintained at the same time. And we didn't really observe much, at least for like the 140 concurrent connection case, but we didn't have like a robust enough server to run it with like thousands of concurrent connections, but that might be spread out over multiple servers anyway. So.
Okay, thank you.
Okay, let's thank our speaker once more.